For section 5.7, we're going to learn how to do some of the normal algebraic operations on matrices. A matrix, again, is just an array of numbers in rows and columns. The first thing we need to know is what the dimension of the matrix is. The dimension is the number of rows by the number of columns. Usually, we'll go the letters M and N. I don't know why they picked two numbers that sound so similar, or two letters that sound so similar, but they did. Now, I'm not actually multiplying these together. It's like if I say, oh, that's a 2x4 piece of lumber. That's what I'm saying here. It's rows by columns, an M by N matrix. Addition and subtraction of matrices is fairly straightforward. We just either add or subtract the elements that are in the same spot, the corresponding elements. For this to happen, that means the matrices have to have the same dimensions. So they have to have the same number of rows and columns. We also have something called scalar multiplication. This is where we multiply the matrix by just a single number, and we just multiply each element by that number. So we're going to deal with some addition, subtraction, and scalar multiplication on this first problem. Usually with matrices, by the way, we use capital letters. So if you see capital letters, think we're probably talking about a matrix. A plus B, well, I'm just going to add these two together. And so what this is, well, I'm first going to check their dimensions. So matrix A has 3 rows and 2 columns. Matrix B also has 3 rows and 2 columns. So their dimensions are the same, so I can actually do this. I can add them together. So my answer is going to be 3 rows by 2 columns. And all I'm going to do is add the corresponding elements. So I mean -4 plus 0. -4. You can go to the next one in the first row, 2 plus 1, 3. Pretty straightforward. 11 plus 5, 16. 9 plus -2, 0 plus 12, -1 plus 0. There you go. There's A plus B. Next one at once is A minus B. Again, exact same idea. But now I'm just subtracting. So -4 minus 0, 2 minus 1, 11 minus 5, 9 minus -2, so that's going to be 9 plus 2, 0 minus 12, -12, and -1 minus 0. And there we go. So nothing crazy there. Next one at once is 3a. That's scalar multiplication. So 3a means what you think it means. Take every element of matrix A and multiply it by 3. So this is going to give me, let's see, -12. Let's see, 6, 33. If it'll let me write, let's get that 6 looking better. And it's not letting me write. That's 33. Let's see, 27, 0, and -3. So that's the 3a part. The last thing it wants is 3a minus 2b. So I need to scalar multiply matrix B by 2. So I'm going to do that off to the side here. So even though it didn't explicitly ask for that, it'd be easiest just to write that out. So 2 times b, just multiply everything by a 2. Now I can do 3A minus 2B. So I'm just taking these two matrices and subtracting them. So negative 12 minus 0, 6 minus 2, 33 minus 10, 27 minus negative 4, 0 minus 24, and negative 3 minus 0. So addition, subtraction, scalar multiplication, not terrible. Nothing crazy going on there. On number 2, add these together. Well, the first one, I checked the dimensions first. The first one has 1 row and 3 columns, 1, 2, 3 columns, whereas the second matrix has 3 rows, 1, 2, 3, and only 1 column. They don't have the same dimension because those numbers are flipped, so this is not possible. You simply cannot add those together. Oh my, I can know how to spell possible. There we go. So I just say, nope, can't do it. Okay. Those are not bad. Matrix multiplication is where things get funky. So let's say I have a matrix that has dimension m by n, and another matrix that has dimension n by p. To be allowed to multiply the matrices together, it is not the same thing as up here where they have to have the same dimensions. What has to happen though is that the column number of the first matrix and the row number of the second matrix have to be the same. That's why I use the same letter. So these numbers must be the same. So that's your check on matrix multiplication. If they are the same, great. Then these numbers, the rows of the first matrix, or the number of rows of the first matrix, and the number of columns of the second matrix, that's going to be the dimension of your answer. That's going to be the dimension of answer. And this is technically how I do it. This is very confusing. What you're going to see is, through example, how we multiply them. This takes some time. We're going to go through it very slow on the first few, but it is not intuitive. So AB, so A times B. I would strongly suggest writing them next to each other. So AB means taking the A matrix, multiplying it by the B matrix. Okay, before I even get started with multiplying, I need to check if I can multiply them. So A is a 2 by 2, B is also a 2 by 2. The middle numbers match. So check, yes, I can multiply them. My answer matrix will be also a 2 by 2. So my answer matrix is going to be 2 by 2. Okay, so here's how I do it. And again, this is very funky. If you've done it before, maybe you remember. If you've never done it before, I'm going to go real slow. I start with the first row of the first matrix and the first column of the second matrix. I'm going to multiply the first number here times the first number here. So 1 times 2. 1 times 2 is 2. plus, I'm going to multiply the second number here times the second number here. 2 times -1, -2. I add those together. That is the first element here. So 2 plus -2 would be 0. You're only going to use rows for the first matrix. You're only going to use columns on the second matrix. So writing these in the correct order does matter. Here's how I do this then. I then move to the second column. So I stick with the first row. I hop over to the second column. And I'm going to do the same process. So first number times first number. So 1 times -1, -1, plus second number times second number, 2 times 8, 16. Add those together, 15 goes here. To know where your answers go, this actually goes back to this. I'm using row 1 and column number 2. This space is in the first row and the second column, row 1, column 2. So if I hop down here now, this is in row 2, column 1. So I'm going to now go to row 2, and I'm going to reset back to column 1. So same process, 4 times 2 plus 2 times -1. So that's going to give me 6. I go to the next column. Remember, on the first matrix, I only use its rows. I never switch to columns on the first matrix. On the second matrix, I only use columns. I never switch over to rows. And so I'm going to have 4 times -1, -4, plus 2 times 8, 16. Add those together, 12. So there's A times B. This will go faster, I promise, as you get better at it, but don't expect it to be immediate. Again, if you've never seen this, it takes a little bit of practice to get used to it. Okay, now, get these out of the way for a second. I'm going to multiply B times A. Again, write it out. So matrix B, 2, -1, -1, 8. Matrix A, 1, 2, 4, 2. Okay, for the first matrix, I only, oops, don't want that. Gotta remember to get rid of that. Go away, there we go. For the first matrix, I only use its rows. I start in row 1. For the second matrix, I only use columns. I start with column 1. So row 1, first number, 2 times 1, 2, plus -1 times 4, -4. That's going to give me -2. Basically, stick with the top row and exhaust all the columns. So I'll move over to the second column. Oh, that's not at all what I wanted. That's what I wanted. 2 times 2, 4. -1 times 2, -2. That goes in the first row, second column. All right, now I've exhausted all the columns. So now I reset the columns. Nope. Just the highlight. There we go. I reset the columns. And I go to the next row down. So this would be -1 times 1, -1. 8 times 4, 32. And I get 31. Exhaust all the columns. So now I'll go to my second column, if I can get this grabbed. There we go. -1 times 2, -2. 8 times 2, 16. And I get 14. This is a very interesting property of matrix multiplication. A times B is not the same thing as B times A. With numbers, that's true. You can flip the order. It's called commutative property. But with matrices, you cannot. I did not get the same answer. So the order actually does matter with a matrix, which way you multiply them. Now, I want A squared. That does not mean square every number in matrix A. I have to actually take matrix A and write it twice. One, 2, 4, 2, 1, 2, 4, 2, and I have to go through the multiplication process again. So rows of the first matrix, columns of the second matrix, so that'd be for the first element, row 1 times column 1, 1 times 1, 2 times 4, add those together, 9. Hop to the second column. One times 2, 2 times 2, add those together. That was row 1, column 2. All right, now I reset the columns, hop down to the second row. Four times 1, 2 times 4, add those together. And lastly, row 2, nope, it's doing so well. Row 2 times column 2. Four times 2, 2 times 2, add those together, 12 as well. So there's A squared, which clearly was not just taking every number in there and squaring it.